Welcome back to our channel, guys. In today's video, we are going to discuss the topic of definite integrals as a limit of a sum, and also we will discuss how we can approximate integrals or find the upper bound and the lower bound of the integrals using the concept of expressing the integral in terms of summation. Okay, so we call it a Riemann sum. We will discuss this topic in detail. Okay, and we will also solve some questions. If you are new to our channel, subscribe to our channel for more contents on JEE Mathematics. So let us begin. So the first topic that we are going to discuss is comparison between summation and integral. Okay, this Riemann summation basically tells us that we can express the integral in terms of some infinite summation. Okay, so integral of fx from x equal to a to x equal to b means the area under the curve, the signed area under the curve of y equal to fx, right? We can express this integral in terms of summation. Summation r equal to 0 to n minus 1, then f of a plus rh times h. This is the area of each rectangle. Okay, so h times f of a plus rh, where r is varying from r equal to 0 to n minus 1. This is the area of each of these rectangles by which we are approximating the area under the curve. So in Riemann summation, we mostly use this type of rectangles, thin rectangles. Okay, rectangular strips we use to approximate the area under the curve. And then when we tend this n towards infinity, this summation approaches the value of the integral. Okay, this is the concept of Riemann summation. So what will be our objective? Okay, to apply this method of summation to find an integral, our objective is to break the region into n rectangles of equal breadth. Okay, so breadth means this dimension, right? This is the breadth of each rectangle. So this is a rectangle. For example, the breadth of each rectangle is h, and the height of each rectangle is f of a plus rh. So if I take this curve, okay, and this is the x-axis like this, then at any point x equal to, let's say, x naught, what will be the rectangle will be like this. Okay, so we can take either this rectangle in the right side of this x equal to x naught point. Okay, so starting from this vertex, we either move left or move right. Okay, so we can actually have two kind of sums that we will discuss later. So if I move from this vertex towards the right hand side, I get this rectangle, right? So what will be the length of this rectangle? This rectangle length will be simply, we can say, f of x naught, because this is the curve y equal to fx. Okay, so this is the concept. Breadth of each rectangle is b minus a divided by n, which is we define as the h. Okay, and height of each rectangle is f of a plus rh. So why this a plus rh? We can say this thing we can derive from the division of interval. Okay, so we divide the interval into n subparts. Okay, objective is to break the region into n rectangles, so we have to divide the given interval x equal to a to x equal to b into n equal subparts. Okay, so like this we can divide. So our h is b minus a divided by 5, right? So we can say b equal to a plus 5h. A is what? A is the left end point and b is the right end point. Okay, and h is the interval length. So a plus rh will be what? A plus rh basically denotes the uh, endpoints of the sub intervals. Okay, so x equal to a plus h will be one endpoint of a sub interval, right? Then we have a plus 2h, then we have a plus 3h, then we have a plus 4h, and finally we have x equal to b in this case, because n equal to 5. Okay, we are dividing this interval into 5 equal parts, and height of the rectangle will depend on our choice of the summations. So let us now discuss about the concept of Riemann sum. Okay, so as we discussed, we divide the region into n number of rectangles. Okay, so let's say if we are given this interval, okay, x equal to a to x equal to b, and this is the curve y equal to fx. So we start from the leftmost endpoint here, x equal to a, right? And then from this point we drop a vertical line upon this curve y equal to fx. Okay, so this vertical line intersects this point. So this point is nothing but a comma f of a, right? From this point we move towards the right side. We move towards the right side, that means the height of this rectangle will be simply the value, the functional value at this point, right? X equal to a, this functional value will be f of a, so this height will be f of a, right? So what will be the area of this rectangle? This breadth is, we discussed this, all these breadths are equal, so they are all equal to h, right? And so we have the area as h time f of a. Then for the next point here, this point is x equal to a plus h, right? So this rectangle, if we construct, this will be, we drop a vertical line here, and then this point, from this point on this curve we move toward the right side. Okay, and then we construct another rectangle of breadth h. So the area of this second rectangle will be simply h times f of the value, the functional value at this point, right? This height will be the functional value at this point, x equal to a plus h. So this will be f of a plus h, right? We stop at this point, right? X equal to a plus n minus 1 times h, or we can say this point is also equal to b minus h, right? So at x equal to b minus h or a plus n minus 1 into h, we have the area of this rectangle as h times f of a plus this n minus 1 times h, right? So this thing we can write as summation h times a plus f of a plus r h, right? Where r is varying from r equal to 0 to n minus 1. So this we call our left Riemann sum. As we are picking only the left endpoints of each subinterval, so we call this sum as left Riemann sum. Okay, so we define this as ln, which is summation r equal to 0. So remember that the summand is basically same for left and right Riemann sum, but the starting points and end points are different. Okay, so for left Riemann sum, r is starting from 0 and ending at n minus 1. Okay, so this thing we need to remember. So this animation I borrowed from Wikipedia to show you that how left Riemann sums are evaluated. Okay, so we can see here we are picking only the left endpoints. Okay, for each subinterval we are picking the left endpoints and then constructing the rectangles to approximate this sum. And we can see here the number of rectangles is tending to infinity. So as the number of rectangles tend to infinity, the breadth of each rectangle is decreasing, right? Because h is equal to b minus a divided by n. B minus a is a constant, so if n is increasing, h should decrease, right? So we can say this is the left Riemann sum. Now let us move to right Riemann sum. Okay, for right Riemann sum we have similar kind of setup, but we are using the right endpoints of the subintervals. Okay, so we again divide the total interval x equal to a to x equal to b into n subparts. Okay, n subintervals, but we choose the right endpoints of each subinterval. So for constructing this rectangle, we pick this point. Okay, x equal to a plus h, not x equal to a. We pick x equal to a plus h. So we get this point, right, by joining this vertical line from this x-axis to this point. We get this point on this curve y equal to fx, right? So then after getting this point, from this point we move towards the left. Okay, for right Riemann sum we move from this points towards the left. So what will be the breadth of this rectangle? Breadth of all rectangles will be same in this case also, right? So h times the length of this rectangle will be what? Length will be simply f of this point, right? The functional value at this point a plus h, so this will be a plus h. So f of a plus h, right? Plus, then if we construct the next rectangle here, then we get this subinterval, right, from x equal to a plus h to x equal to a plus 2h. Okay, So then we again get this point on this curve y equal to fx and then move towards the left. So we uh, construct this rectangle here. So what will be the height of this rectangle? Height will be f of a plus 2h, right? And width or the breadth will be simply h. So then we simply sum all of the areas of these rectangles. We get finally h times f of the value at the rightmost point. Okay. So functional value at x equal to b, or we can say a plus n h, right? Because we discussed that b minus a divided by n is equal to h, right? So we can write this as b equal to a plus n h, right? So this thing we can write as the summation of h times f of a plus rh, where r is varying from r equal to 1 to n, right? So this thing we call the right Riemann sum. Why right Riemann sum? Because we are using the right endpoints of each subinterval. Okay, so this is the concept. Now here is a similar animation from Wikipedia demonstrating the right Riemann sum. We can see here we are picking the right endpoints of each subinterval, right? And as the number of subintervals is getting larger and larger, the width of each rectangle is getting smaller and smaller. So when this thing, the width of each rectangle tends to 0, or we can say by the relation h equal to b minus a divided by n tends to infinity, the sum of areas of all the rectangles converge to the value of the integral, okay, which is integral a to b f of x dx. The question is, what is the relation between ln, rn and I? Okay, I is the actual integral. We discussed I is integral a to b f of x dx, right? This integral is, we are calling it I, okay? And ln is summation r equal to 0 to n minus 1 h times f of a plus rh, okay? The left Riemann sum, and rn is the right Riemann sum, this times h, okay? So what will be the relation between these things? Remember, for this ln and rn, we are not using the limit, okay? Because at the limiting case, when n is tending to infinity, the value of ln and rn at n tending to infinity will be equal to I. That's it. So we cannot compare them, because at n tending to infinity, all of these quantities will be equal. So we compare them when n is not tending to infinity. Okay. So we are talking about finite summations. Remember, we are not talking about infinite summations. Okay. We are not taking the case n tending to infinity, but we are taking some finite number of subintervals. Okay. And then we discuss the cases. So let us see what will be the relation between these quantities. Okay. So this is the relation between ln, rn and the actual integral. Okay. We can see this by an example of increasing function. Let's say we take the increasing function like this. Okay. So if I take any interval here from x equal to a to x equal to b here, okay, and then we calculate the left Riemann sum. So let us take a bigger picture here. So let us take this graph here. Okay. And then we take this interval here, and then we simply take the case n equal to 3. Okay, a simple case to understand. So this function is increasing, right? Fx is increasing in this interval a to b. So we divide first the interval into 3 equal spaced subintervals. Okay, so then we construct the rectangles. For left Riemann sum, we take this left endpoints of each subinterval. So we construct this rectangle, and then this rectangle and this rectangle. Okay. So our ln will be this summation. And we can clearly see the area under the curve fx from a to b is clearly greater than this summation, right? This ln. So we can say ln is this white area, right? And then if we calculate the right Riemann sum here, we get this region. So Let's change the color a bit. Maybe we can take blue color. Okay, so this blue region I am sketching here. This blue region is this total region. Okay, bounded by this blue rectangles. So we can say this blue rectangles, the total region bounded by them will be Rn. So this area is blue colored, and this is, we can see clearly, greater than the actual integral. Okay, because actual integral is this yellow region. Okay, so this region is the actual integral, yellow region. I is this yellow region. Okay, so we can clearly see and compare these things ln, I and Rn for increasing function, and similarly you can check for decreasing function by constructing the rectangles and checking it yourself. Okay, but remember, when we are taking the case n is tending to infinity, taking so many subintervals that width of each rectangle is tending to 0. Okay, h is the width of each rectangle and h is tending to 0, or we can say n is tending to infinity. Then we say that ln and Rn both converge to this value of integral. So what is the summary of all the things that we discussed till now? So the Riemann sum, or expressing the area under a curve y equal to fx by summing up all the areas of rectangles. For this thing, we have to first break down the given region into several thin rectangles. Okay, and we have two different scenarios to deal with, right? The two topics that we saw in the beginning of the session: limit of sum in terms of a definite integral, and the second thing is the approximation of a definite integral. So remember, when we have to find the limit of the summation as n tends to infinity, we have to find the limit, then we have to solve the definite integral. Okay, and when we have to approximate the integral with some summations, then we are summing up all the areas of this n rectangles. Okay, so we are talking about a definite integral or integration when we have to find the limit of the summation, and when we are told to approximate a given integral, we are breaking down the region into n parts and then summing up all the areas of the rectangles. Okay, this will be our approach to deal with the problems. So these two topics are closely related to each other. In the first part of this session, we are primarily discussing about this topic here. Okay, approximating the integral using the Riemann sum, or the left Riemann sum or right Riemann sum. Okay, and in the second part we will discuss about the limiting case where n is tending to infinity and we have to find the limit of a given summation, and then we will use the concept of definite integration. Okay, that's it. So we have a question from JEE Adv 2008 based on this concept of Riemann sum and comparison of this right Riemann sum, left Riemann sum, and then the actual integral. Okay, so what does this say? Let Sn equal to summation of this thing from k equal to 1 to n. Okay, and Tn is summation of the same thing from k equal to 0 to n minus 1. So we can see clearly we have a hint that we are using the concept of Riemann summation to compare this sigmas. Okay, because here we have this k running from 1 to n, which is a hint of the right Riemann sum, right? And this thing k equal to 0 to n minus 1, this is giving us some hint about the left Riemann sum. Okay, so we are trying to interpret this summation. So what did we discuss? We discussed that we are calculating this summation for a summand which is of the form h time f of a plus rh, right? F is some function. Okay, so let us express this given summands in terms of some h times f of a plus rh. Okay, this a and h we are free to choose. Okay, so let us take this n divided by n square plus kn plus k square. So we have to express this in terms of h times f of a plus rh. What is h? H is equal to b minus a divided by n, right? So b minus n divided by n f of this thing is a plus r times b minus a divided by n. Okay, so we can see here this r is playing the role of this k, right? So we can replace this with k, so this becomes k. Okay, so here we have to somehow find this term, right? B minus a divided by n. So we have to first get an extra n in the denominator, right? So we can try to pull an n from the denominator. So we get n in the numerator and divided by, so this n, we actually take the n square out of this denominator. Why? Because there is an n in the numerator, so one n will be cancelled and we will have only one n in the denominator, right? So this thing we can write as 1 divided by, this will be 1 plus, this will be k divided by n plus this will be k by n whole square, right? Now this thing we can cancel, so this becomes 1 by n times 1 divided by 1 plus k by n plus k by n whole square. Now look at this thing. Okay, inside this bracket, if we look into this thing, we can say this k by n is generated, right? So k by n is here also and here also, right? So this thing is created. Now the question is how we can choose this a variable and b variable, right? So we can see we need a function of a plus k times b minus a divided by n. So it will be better if we somehow vanish this a variable. Okay, so we put this a variable equal to 0. Okay, so put a equal to 0. Then we have the coefficient of k by n here as b minus a, right? But b minus a equal to 1, right? Because we don't have anything with k, we have simply 1. So b minus a, so b minus 0 will be 1. That means b equal to 1. That means we have to somehow relate this summation with integration from limits x equal to 0 to x equal to 1. Okay, so what will be our integral? Our integral will be 0 to 1. Then we have this thing, right? B minus a divided by n we discussed. So this thing easily can be written as b minus a, right? 1 we can write as b minus a. So this thing is created. Now what will be our f of x? We discussed f of this thing is this expression, right? This variable part. So this thing will be our simply f of k by n, right? So we have to replace k by n with x. So this thing will be f of x dx. So this integral we can write as integral 0 to 1. We have to find the fx. So fx will be what? Fx will be simply this thing, 1 divided by 1 plus x square. Okay, so dx divided by 1 plus x square, right? So we have to find this integral. Now this thing you can calculate easily. When you calculate this integral becomes equal to pi divided by 3 root 3. Okay, this you can calculate yourself. But now we have to compare the Sn and Tn with this integral value, right? So how do we compare? We discussed this sum and this sum, they both are the Riemann sums for this integral, right? So this thing Sn is the right Riemann sum of this integral and this thing Tn is the left Riemann sum of this integral, right? Now how do we compare them? By using this relations, right? If f is increasing function, we can say ln is less than I and less than Rn, and if f is decreasing, Rn less than I less than ln. Okay, so this thing Sn will be our Rn here and this Tn will be our ln here. Okay, so to compare them we have to simply check the nature of this function fx. Okay, so let us check this function fx equal to 1 divided by 1 plus x square. Okay, so if we check the derivative here, this will be 2x plus 1, right? So we can see from x equal to 0 to x equal to 1 our derivative will be negative, right? in this interval fx is decreasing. So fx is decreasing, that means this left Riemann sum will be definitely greater than the actual integral, right? And this actual integral is greater than the right Riemann sum. So we can say this I, which is pi divided by 3 root 3, this thing is less than our Tn, and this pi by 3 root 3 is greater than our Sn. Okay. So if we choose the correct options here, Sn less than pi divided by 3 root 3, yes, this option will be true. This option will be wrong. And Tn greater than pi by 3 root 3, this option will be true and this option will be false. That means A and D will be our correct options. Okay. So this is how we compare the Riemann sums. So we have this question here. Let fx equal to e to the power root x for all x greater than equal to 0. Okay. Define I equal to integral 1 to 4 f of x dx. Select the correct statement about this I. Okay. So we have to uh, choose the correct statement. This is a correct type question, single option correct type question. So only one option will be correct. We have to choose the correct option. Okay. So for this question, let us first try to draw a rough graph of this function fx. Okay. So let us draw this. So we have our fx as e to the power root x, right? So we check the derivative of this function, e to the power root x times 1 by 2 root x, that is positive for x greater than 0, right? And we are talking about x equal to 1 to x equal to 4, so we have to only bother about this interval. Okay, x equal to 1 to x equal to 4. So we can say this graph is increasing, right? And if we check the concavity of the graph, let's check, f double dash x will be half times e to the power root x outside, then we have here it will be 1 by 2x, then we have minus 1 divided by 2 x to the power 3 by 2, that means x root x, right? So this thing we can write as f double dash x as e to the power root x divided by 4 root x times x. Okay, so 4x root x times root x minus 1. So this thing is again positive, right? This is positive in this interval x equal to 1 to x equal to 4, because this root x minus 1 is positive, right? And every other thing is positive here. So we can say this function is concave upwards, right? So the graph will look like this in this interval. So let me draw it correctly. It says something like this. Okay, this is the point x equal to 1, this is the point x equal to 4. So then we try to approximate this integral by Riemann sum first. Let us try. So how many intervals should we take? Let us take two intervals first. So we divide this interval into two equal parts. X equal to this point, midpoint of this interval will be x equal to 5 by 2, right? So this thing we join and then we construct the rectangles. So we can say I is less than equal to something and greater than equal to something. Okay, so what will be this thing here? This thing in the left side will be the area of this two rectangles. Okay, the sum of areas. So this will be, this point will be, this height will be e to the power 1, right? So e, this thing will be e to the power root under 5 by 2. So the sum of areas will be e times this will be 3 by 2. So 3 by 2 times e to the power root under 5 by 2 plus e, right? If we draw the right Riemann sum here, we construct this rectangle here. like this and then like this. Okay, so this will be e square and this will be e to the power root 5 by 2, so 3 by 2 times e to the power root under 5 by 2 plus e square. Okay, so our I lies in this interval. Okay, but if we check for the C option, we cannot tell whether this option is correct or not by this method, right? The expression is different, so we have to think in some other way. So remember, whenever we are told to approximate a integral or some area under a curve, it is not necessary that we can only use rectangles. We can try any other possible curves like trapeziums, right? So we can approximate this integral by trapeziums, by forming trapeziums. Now the question is, how will we form the trapeziums here? So if I take this point here, the midpoint of the interval 1 to 4, then we get this point, right? This 5 by 2 comma e to the power root under 5 by 2. So from this point we join this point. Okay, this two vertices we join together. Then this thing, this a, this b, this c and d, this abcd is a trapezium, right? So we can approximate the area by summing up the area of these two trapeziums. The other trapezium will be like this, right? This point is E, this point is F. Okay, so CBEF will be another trapezium. We join this point with this point. Okay, so let us draw this diagram a little bit clear. So we have this graph. Okay, x equal to 1 to x equal to 4, right? So x equal to 4 will be like this. Then we try to break this interval into two different parts or three different parts or four different parts and so on. Okay, so we have to decide how many intervals we should take. Here we can see these values, right? E to the power root 2, e to the power root 3, then e to the power 2 we can write as e to the power root 4, right? This e to the power 1 we can write as e to the power root 1. So basically they are the values, the functional values at the point x equal to 1, x equal to 2, x equal to 3 and x equal to 4. So if I want to check the A and B options, we can say we have to somehow get these points, right? X equal to 2, x equal to 3, x equal to 1, x equal to 4. So to get these points, we have to divide this interval into three parts, right? This point is x equal to 2, this point is x equal to 3. Then if we want to construct the trapeziums here, so these points we join, then we simply construct the trapeziums. Okay, these three trapeziums will be like this. Now the catch is, when we are summing up the areas of the trapeziums, this line here, for this trapezium, let's take, okay, let's take this trapezium, the rightmost trapezium here. If I take this line here, this line will be either above this curve y equal to fx, or below this curve y equal to fx, right? Now what is the factor that decides whether this line will be above or below? That is the question. The factor that determines this condition is concavity of the graph. Okay, so we have to check the concavity of the graph. If the function is concave upwards like this, okay, for this function fx is concave upwards, right? We discussed f double dash x is greater than 0 in this interval, positive. So that means this function is concave upwards. Okay, so if the function is concave upwards, this line will be always above the curve y equal to fx, right? So the area of this trapezium, we can see clearly the area of this trapezium will be greater than the area between x equal to 3 to x equal to 4, right? And same goes for this, because here the graph is also concave upwards and also here the graph is also concave upwards. That means our total integral will be always less than the total sum of areas of all the three trapeziums. So let us sum them up. So we get the total area of the trapeziums will be half times sum of parallel sides times the difference or the distance between the two parallel sides, right? So this will be half times this functional value is e to the power 1, right? So this is e, this parallel side length are e, and this will be e to the power root 2, right? And this thing will be e to the power root 3, and this thing will be e square, right? So this we can write as half times 1 times e plus e to the power root 2. So e plus e to the power root 2, right? The area of the first trapezium plus half times 1 times e to the power root 2 plus e to the power root 3 plus half times e to the power root 3 plus e to the power 2. Okay. So e to the power root 3 plus e square. That means simply becomes half times this we can simplify as e to the power root 2 times 2. So this 2 and half gets cancelled. That means we can write this thing as e to the power root 2 plus e to the power root 3. Here because we have 2 e to the power root 3 plus then we have e plus e square divided by 2. Okay. E plus e square divided by 2. So we can see clearly this matches with option A. So option B is definitely false, right? I is not greater than equal to this quantity. I is less than equal to this quantity. Okay, because the graph is concave upwards. The graph of fx is concave upwards. And option C, we don't need to check because this is a single correct type question, so only one option will be correct. But for our understanding, if we try to check this, we can see here this e to the power root under 5 by 2, this value will be obtained when we choose the point x equal to 5 by 2, right? So like the previous case that we just discussed, we tried using the Riemann sum approach. Then we took x equal to 5 by 2, the midpoint of the interval 1 to 4. So this thing you can also check by the trapezoidal approximation here, constructing the trapezium for two subintervals like this. So we have, let's say, this graph and this is the midpoint. So we just join this point with this point and this point with this point, right? So the area of the trapezium, the total area of the two trapeziums will come out to be exactly this value. Okay. So this thing you can check, the total area of the trapeziums will be greater than this I. Okay, that's why option C is going to be false, because I is not greater than equal to this value, I is less than equal to this value. Okay, and we cannot say anything about this I. This is false. So the correct option in this case will be option A. Okay, this is how we use our understanding of interpreting this area under a curve as summation of geometrical curves, summation of areas of geometrical curves. Okay, that's it. So let us discuss the method of finding limit of the sum. Okay, till now we were discussing about expressing the integrals as a sum, as a finite sum, okay, and comparing them. But now we are interested in the limiting case. Okay, when n is tending to infinity, so the area converges, the area of the all the rectangles or all the figures that we were taking, like trapeziums, rectangles, etc., the total area converges to the integral of the function from left endpoint to right endpoint. Okay, so we have to evaluate either of these limits, right? Both are same for the limiting case we discussed. So to find the limit or the limit of the sum as a definite integral, what we have to do, let us understand this. We simply find an expression in terms of this. Okay, so these expressions are nothing but h times f of a plus rh. We just use the expression for h. Okay, h is equal to b minus a divided by a. That's it. So we first arrange the limit in this form. Okay, in terms of summation, we are summing something. Okay, and this is the variable factor here r, or it may be k. it may be given in the question in sigma format, or we have to somehow derive the sigma format. That is the game here. Okay, then we simply replace our r divided by n. So we are expressing this summation as summation tr. Okay, this sum is running over this variable r. So this variable divided by n, r by n, we are replacing with x, then 1 by n with dx, and then we are replacing the summation with integral sign. Okay, definite integral sign. Now how to find the lower and upper limits of the integral? Let's say in the summation form, r is ranging or r is varying from a to b. Okay, capital A to capital B. Then what will be our lower limit? Lower limit will be limit n tending to infinity a divided by small n, and upper limit will be limit n tending to infinity b divided by small n. Okay, so let's say we have r varying from r equal to 0 to n minus 1. What will be our lower limit of the integration? This will be simply limit n tending to infinity 0 divided by n, that is 0 only, right? And what will be the upper limit? This will be limit n tending to infinity n minus 1 divided by n. Okay, this limit is equal to 1. And similarly we can check r equal to 1 to n, this case. So this thing becomes limit n tending to infinity 1 divided by n, right? This also becomes 0. And then limit n tending to infinity n divided by n becomes simply 1. So we have the same limits for both of these cases. Okay, but what will be the case when, let's say, r is varying from r equal to 0 to 2n? What will be the case? So we can find the lower limit of the integral by putting limit n tending to infinity 0 divided by n. Okay, this is 0. And what will be the upper limit? This will be simply 2n divided by n, this limit. Okay, when n tending to infinity, this will be simply 2. That's it. So we have to integrate from 0 to 2. Then we simply perform the definite integral and we get our answer, the limit of the summation. Okay, let us do some problems. So it is given that the sum of this series is 1 minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square plus so on up to infinity. Okay, so infinite terms are there. The sum of this series is pi square divided by 12. This information is given to us and we have to find the value of pi square log e with base l if l is equal to this limit. Okay, so remember, in most of the cases we will be given some limit, and it will not be obvious that we have to find the limit of the sum using our concept of definite integration. It will not be obvious. Okay, we have to practice as many questions as possible so that we can see that, okay, in this question we have to apply the limit of some concept. So this is a matter of practice only. Okay, so what was our plan for this type of questions? Our plan was to first arrange the given expression in terms of some sigma. Okay, so this expression here is a product expression, right? So what will be our strategy to convert some product into a summation? That is the question. Okay, so let's say I have three terms here, a1, a2 and a3. If I want to change the product into summation, what we have to do? The simplest method we have here is taking log. Okay, because log we can apply to this term so that this terms become simply log of a1 plus log of a2 plus log of a3, right? So log of this product becomes simply summation log, right? This is the concept that we have to use here. So let us apply this. So we can first write this expression in terms of product form, product notation. Okay, pi notation, capital pi notation. Let us write them. So this will be product of 1 plus this thing we can write as r divided by n whole to the power 4, right? Because here r is 1, here r is 2, r is 3. Here we can see r is equal to n. Okay, so when r is equal to n, 1 plus 1, so this becomes 2. And then we have this raised to the power 1 divided by r, right? Then r is running from what to what? R is running from r equal to 1 to r equal to n, right? So this thing is limit n tending to infinity. This is our L, right? So we have to first express this product in terms of summation. So we take log both sides with base e here. So log L with base e, this becomes simply limit n tending to infinity summation r equal to 1 to n, then 1 divided by r log of 1 plus r by n whole to the power 4. Now what is the next step? We have to somehow find some expression in terms of r divided by n, so that we can replace the r by n terms with x. So we have to somehow create this 1 by n here, right? This term 1 by n is missing from here. So we create this 1 by n. So we have to multiply by n also, right? So we can see clearly this n divided by r, we can take in the denominator and write it as 1 divided by r by n, right? Now see, a very clear pattern is generated here. This r by n, this r by n here, and 1 by n outside. So we can take this 1 by n outside the summation, because r is running from 1 to n, this sigma is running over the variable r, so n is treated as a constant. Okay, so this thing is a expression in terms of r by n only. This is our f of r by n. Okay, so we replace the r by n with x and this 1 by n with dx and summation with integral sign. So this thing becomes simply integral, then log of 1 plus x to the power 4 divided by x dx. Okay, what will be the limits of the integral? The limits will be simply from 0 to 1, right? We just discussed this. If we have r equal to 1 to n, or if we have r equal to 0 to n, in all of these cases integral limits will be 0 to 1. So we have to somehow find this integral. Okay, so how do we find this integral? So we can simplify this integral a little bit. Okay, we can multiply and divide by x cube here. So x cube will be this. This term becomes x to the power 4 and its derivative becomes 4x cube. Okay, so this thing is created in the numerator. So this thing simply becomes integral 0 to 1, then log of 1 plus t divided by t dt with 1 by 4 multiplied outside. Okay, so we have to find this integration. Now this integration is not a standard integral. Okay, this integral we have to find using somehow this information. That's why this information is given to us. Okay, so how to use this information here? Think about this in terms of series expansions. Yes, you are right. We have to use the series expansion of log of 1 plus t. Okay, so log of 1 plus t, if we expand, this log of 1 plus t is simply t minus t square by 2 plus t cube by 3 minus so on up to infinity, right? So what will be our log of 1 plus t divided by t? This will be simply 1 minus t by 2, right, plus t square by 3 minus so on up to infinity. So what will be the integral from 0 to 1? We can say the integral will be 1 minus, this integral will become half times 1. That means 1 by 2 square, right? The next term will become 1 by 3 square, right? Minus, we have the next term 1 by 4 square. Okay, like this. And if you closely observe, this is the series that is given to us in the problem statement. Okay, so this value is given to us as pi square by 12. So we have to use this. So this value, this L, or this value is log L, right? So log L is equal to pi square divided by 48. So what we have to find here? Pi square log E with base L, right? So pi square log E with base L, this becomes simply pi square log E with base E divided by log L. with base e, right? So the value of log L with base e, the natural log of L is already known to us, right? This is pi square divided by 48, and this is 1. That means pi square divided by pi square times 48. So pi square gets cancelled. Our answer becomes 48. So what will be our correct answer here? 48. Okay. So this is how we use the concept of limit of a summation. Okay. Next we have a question from JEE Advanced 2016. Okay. Here it says let fx equal to limit n tending to infinity this thing. Okay. For all x greater than 0. Then we have to find which of the options is or are correct. Okay. So obviously this is a question from using the concept of definite integral as the limit of a summation. So we first have to express this limit format into some summation format. Okay, limit n tending to infinity some summation. So let us try. So this thing is some product, right? So let us write in capital pi notation first. So we can write this thing limit n tending to infinity. Then we can write, now if we look carefully into this expressions here, n to the power n divided by n factorial. Okay, so this we can write as n times n so on up to n times, right? Divided by n factorial we can write as n times n minus 1 times n minus 2 so on up to 2 times 1, right? So this thing we can write as product of n divided by r, right? From r equal to 1 to r equal to n. So let us write this. So product of this n divided by r from r equal to 1 to n. Then we have here product of this thing, this numerator part we can write as product of x plus n divided by r, right? Where r is running from r equal to 1 to n. Then the denominator we can write as product of this x square plus n square divided by r square, right? So we can club these products together, right? Because they are operating over the same range of r, right? R equal to 1 to r equal to n, they are operating. So we can combine them. That means we can write this as limit of this thing as n tends to infinity, product of r equal to 1 to n, product of n divided by r times x plus n divided by r divided by x square plus n square by r square. Okay, whole to the power x divided by n. Now this is our fx. So what we do, the next step will be obviously taking log both sides. Okay, so we can write this log of fx equal to limit n tending to infinity. Then we can take log here, so this product will be converted into sigma, right? So this will be x divided by n will be outside, then log of this n by r times x plus n square by r square. So n by r times x plus n square divided by r square divided by x square plus n square by r square with summation running from r equal to 1 to n. Okay, so let us go to the next page here. That means we got log of fx equal to limit n tending to infinity x by n summation r equal to 1 to n log of this thing we can multiply r square divided by n square in both numerator and denominator. Okay, so this thing will be rx by n plus 1 divided by this will be r square x square divided by n square. Okay, so r square by n square times x plus 1. Now we have to convert this into a limit of a sum. Okay, so what will be our steps here? Steps will be simply replacing this r by n with some variable. In this case x is already used, so we we will use, let's say, t, for example. Okay, any other variable. So log of fx will be limit n tending to infinity summation. So this limit will be omitted, so this summation becomes integral, and this x is outside. Okay, so x, then integral 0 to 1, right? Because this limits will be similar like the previous case. So this will be 0 to 1 integral. This will become log of 1 plus tx divided by 1 plus t square x square, right? Dt. So now we have to somehow simplify this expression. So there is some obvious substitution. I hope you are also getting it, the substitution hint, that this x is treated as a constant, right, in this integral. So we can substitute this xt as some variable u. Okay, so that this x dt becomes our du. Du becomes x dt. So we can write this as integral 0 to, then upper limit will be x, right? Then we have log of 1 plus u divided by 1 plus u square du. So this is our log of fx. So fx is e to the power this thing, right? So fx is positive by default. So let us check the options here. In the options, we are to check whether this holds true, this holds true, or this holds true. Okay, or we can say we have to check the signs of this f dash 2 and check whether this f function is increasing in this range 1 to half or 1 by 3 to 2 by 3. So this D option is the easiest among all the options, right? Because this is the form f dash x by fx, and as we have already created this log of fx form, we can differentiate both sides with respect to x using the Leibniz rule, right? So this thing, if we differentiate both sides, we get f dash x divided by fx. See, this form that we needed to check option D is already created here, right? F dash x divided by fx. So let's check f dash x divided by fx will be, using the Leibniz rule, it will become log of 1 plus x divided by 1 plus x square, right? So we have to check the values of simply f dash 3 by f3. That means this will be log of 4 divided by, this will be 10, and then f dash 2 divided by f of 2 equal to log of, then we can substitute x equal to 2 here, so this becomes 3 divided by 5. Okay, so this is nothing but log of 2 by 5, and this is log of 3 by 5. Both are negative, right? Because the argument inside the log is less than 1. So which one will be bigger in this case? We can say clearly this thing will be bigger, right? Because log x is an increasing function. So if we check by the graph here, this is the graph of log x, right? So x equal to 2 by 5 is here, x equal to 3 by 5 is here. So that means if we compare this log values, log of 3 by 5 is greater. Okay, that means this option says that f dash 3 divided by f3 is larger. That means this is larger, that is false. Okay, so this option is false. Now we have to check option C. Okay, because A and B are of the similar types and they require the nature of this fx function, but we don't have this fx function yet. We have log fx, so fx will be e to the power this integral, but this integral we cannot simplify further, right? So we have to put some effort in understanding the behavior of this function log of 1 plus u divided by 1 plus u square. So we prefer to check the C option. This is the next easiest option. Okay, so f dash 2, we can say f dash 2 by f2 is our log of 3 by 5, right? So what will be f dash 2? F dash 2 will be f2 times log of 3 by 5, right? This f of 2. Now see, fx is positive because it is e to the power something. So this thing is positive, this thing is negative. So this becomes negative. Okay, f dash 2 is negative. or we can say if f dash 2 is negative, f dash 2 less than equal to 0 is also true, right? So option C will be definitely correct. So now if we try to check the option A and option B here, we have to check the nature of this function. Okay, so from this equation we can write f of x is e to the power this thing, right? Integral 0 to x log of 1 plus u divided by 1 plus u square du. Okay, so this thing we can check easily. F dash x will be equal to this thing is e to the power this thing, okay, times the derivative of this we can find using the Leibniz rule. So this will become log of 1 plus x divided by 1 plus x square, right? So we have to check the nature of this derivative in 0 to 1. Okay, so let us check. In this interval, this 1 plus x is greater than equal to 1 plus x square, right? We know that if we have a number less than 1 but greater than 0, if we square the number gets smaller, right? So this thing we can say 1 plus x is greater than equal to 1 plus x square, and equality holds true when x equal to 1. That's obvious. So that means we have this f dash x as some positive function, right? Because if we have the argument inside this log 1 plus x divided by 1 plus x square greater than equal to 1, this thing will be definitely greater than equal to 0. That means f dash x is greater than equal to 0, which means fx is increasing function. So if x is increasing function, that means the value at x equal to 1 will be definitely greater. Okay, so this option is clearly wrong, and the value of f at x equal to 2 by 3 will be definitely greater than equal to f of 1 by 3. So this option will be correct. That means B and C option are our correct options in this case. Okay, this is how we solve this problem. Now let us move to this problem here. So this is the last problem of this session. Here it says let s equal to this sum. Okay, so then we have to choose the correct statements about s. Okay, for this question let me tell you that the idea is a bit different. Okay, so till now we were approximating the integrals using summations, using Riemann sums, and constructing rectangles or trapeziums, right? But now the situation is reversed. That means we have to approximate a given summation using integrals. The situation is actually reversed. Okay, we are given some summation and then we have to find the upper bound or lower bound of this summation using integrals. So how can we do it? So our method will be purely geometrical. Okay, we have to somehow interpret this given summation geometrically. So how can we interpret this? Let us use the concept that we were using in the Riemann sums. Okay, we were constructing some rectangles with equal width, right? So that is the motive behind this approach, because here we have equally spaced numbers, right? The difference between each of them is 1. So 1 0 0 0 1, then 1 0 0 0 2, 1 0 0 0 3, so on up to 15,999 and then 16,000. Okay, that's it. So that is the motivation behind our approach. So let us try this. So obviously the thing that we can do here is drawing the graph of y equal to 1 by root x. Okay, because these are of the form 1 by root something. So we can draw the graph of 1 by root x first. So graph of 1 by root x looks something like this. Okay, that means if we try to enlarge this graph first, let us enlarge this. So let us take the region, this let's say 10,000 to 16,000. Okay, then we have the graph like this, almost flat, right? So we can draw this. Now if we check, this is some area of a rectangle, okay, with side length 1 divided by root under this, and the other side length is 1. So we place the points here first. this will be 10,001, and this point is 15,999. Okay, so this rectangle, if we consider, this rectangle will be simply this. Okay, like this, for example. So we can construct two rectangles about this point, right? Either this side or this side. Now this is the main idea. As we can get two rectangles, that means we have two bounds. Okay, two bounds, that means upper bounds and lower bounds. So if we go like this, okay, this area is 1 divided by root under 10,001 times 1. Okay, and the next area will be what? This point is 1,002, right? That means this second rectangle will be clearly having the area 1 divided by root under 10,002 times 1, right? So this second term, it is generated here. So we can say, if we go like this and we construct this rectangle here for the last point 16,000, and in the same direction. So remember, we are choosing the same direction. Okay, that is important, because we don't want that any of these rectangles mix up with each other. Okay, we want them to cover separate areas so that we can add them. Okay, so the direction will be same like this, and this graph will continue like this. Okay, 1 divided by root x, let us draw it again like this. So this total yellow region is our S, right? So in between we have many rectangles. So S is our yellow region. We can say S is surely greater than equal to the integral of this function 1 by root x dx from x equal to 10,001 to 16,001, right? So this will be 10,001 to 16,001. Okay, so what will be this value if we calculate? S greater than equal to, this will be 2 root x, so 2 under root 16,001 minus 10,001. Okay, now in the options we are given something like 220. Okay, so 220 is what? How can we get this done? 220, we can get this when we have 2 times 110. Okay, why this 2 we needed here? We needed this 2 for this thing. Okay, so then if we try to generate 110, we can say this 110 whole square is clearly greater than this 10,001, right? That means if we take square root both side, this 110 is clearly greater than 10,001, right? That means we have here, if we uh, multiply by negative sign both side, we get minus under root 10,001. That means we can say 2 times under root this 16,001 minus 110, this is clearly less than this 2 times under root 16,001 minus under root 10,001, right? But now we have a very interesting thing. Okay, so the right hand side is larger. Okay, and we already discussed that S is greater than equal to this thing, the right hand side. Okay, now this right hand side is already greater than this number. That means S should also be greater than equal to this number, right? So 2 under root 16,001 minus 110, right? So this we can write as S plus 220 greater than equal to 2 under root 16,001. Okay, so that means option A is correct, option B is wrong. So we have to check option C and D also. Okay, so let us check. Now for this thing, we can check by constructing the other rectangles. Okay, so let us construct this other rectangles in the opposite side. So from this point we travel towards the left side and construct this rectangle. Okay, So the area of this rectangle will be again same, 1 divided by root under 10,001, but the sum of the areas of all the rectangles in this case will be less than the integral. Okay, so this thing, the second rectangle will look something like this. Okay, and the last rectangle we have like this. So we can say our S is this blue region. Okay, so S is blue region, that means the area of the blue region is clearly less than equal to the integral of the function 1 by root x from x equal to 10,000 to this point, right? 16,000. So this becomes, if we calculate S less than equal to, this thing becomes 2 times under root 16,000. So this becomes under root 16,000 times root 10. That means this is 40. Okay, so 40 root 10 minus 100. Okay, that means S plus 200 is clearly less than equal to 80 root 10. So which option will be correct? S plus 200 is less than equal to this thing. That means option C is wrong and option A and D are the correct options for this problem. Okay, so this is the idea behind this thing. Sometimes we have to approximate the sum in terms of an integral, and sometimes we have to approximate an integral using summations. Okay, so these variations we can expect in this concept. So that's all for today's, guys. I hope you have enjoyed this session and understood all the things that we discussed in this session. The session PDF I will share on our Telegram channel. Okay, do like, share, and subscribe to our channel for more contents like this.